Having done all of this regarding choosing scales, let us now choose a scale for our foregoing case. Watch the screen to find that table we have been trying to deal with. To start, let us choose a scale for X, for this axis. Now, back to what we've been using. Scale is approximately equal to the number with the highest magnitude on that axis over number of usable intervals. Let's choose a scale for this X, like I said before. The values of X range from -3 to 2. Which of these values will be used to choose a scale? That is, with respect to this X-axis, which number is this H? Is it -3? Is it -2? Is it -1? Is it 0? Is it 1? Is it 2? Don't forget that H is the number or the figure with the highest magnitude without direction being put into consideration. With direction being put into consideration, 2 is the highest, because someone that has 2 is richer than somebody that is owing 3. But forget about signs. Which number then has the highest magnitude? It is this 3. Therefore, it is this -3 we're going to make use of to make a scale for this X-axis. This X-axis. That is why we're going to replace this H by 3. And then, what about this T? It is number of usable intervals from this origin to the edge of the axis. We are paying more attention to this negative side of the X because we're using -3 for it. If it is 2 we're using to make this scale, I would have been able to concentrate on this side. But as it were, it is this side we are concentrating on. Let's continue. How many usable intervals are there from here to here to make T? Let's count. First, let us get how many intervals from here to the edge. From here to here, 1 interval, 2 intervals, 3 intervals, 4 intervals, 5 intervals, 6 intervals. Don't forget what I said earlier. We should not use all available intervals from the center, that is origin, to the edge of the graph page. Because of emergencies, we have to cut off either 1 or 2 intervals. These emergencies you will see in practice. But as for now, just know that for emergencies, we don't use all the intervals from the origin to the edge of the graph page. Let us cut off 1. Since from here to here contains 6 different intervals, we're going to make use of only 5. That is, cut off this last one, so we can use 5 intervals, counting from here to here. How many are there? 5. Let's count again. 1, 2, 3, 4, 5. That means that our T is equal to 5. I hope you are following what I'm doing right here. Let's make progress. Now we have got the value of H as -3, and we've got the value of T as 5. Let's try to get the value of the scale. This is how we arrived at scale is equal to 3/5. In fact, approximately equal to 3/5. Don't forget that the preferred scale is a whole number. That is how, at last, we get this scale is equal to 3/5. Don't forget that this H is 3, I did not write -3 here because we are not interested in the direction. We have interest only in the magnitude. That is why this 3 is not -3. Let's continue. And then this t became 5. Don't forget. Certainly, we're going to get a decimal after dividing this 3 by 5. First, let us try to get the answer before we think about deciding to manipulate or not. Now we see that the scale is equal to 0.6. Please confirm. 3/5 is equal to 0.6. Confirm. At this point, please, do you think that this 0.6 is among the preferred scales? Yes, it is. That means we can start using it. But can we make it better? Don't forget that this is second class among the acceptable scales. The 3 categories of scales that we accept as usable are, first and foremost, whole numbers. That is, if a scale falls among the preferred scales, then we choose that it is a whole number. If it is not possible for us to make a scale a whole number, we try the next one, which is a decimal with 1 decimal place. It is either a pure decimal or a mixed number with 1 decimal place. If it doesn't work that way, we can try 2 decimal places. But we know, because we heard before, that once it enters 3 decimal places, it becomes difficult to use such scale to calibrate an axis. But at a glance, make your choices with the first choice being a whole number, second choice, a decimal with 1 decimal place, then third choice, a decimal with 3 decimal places. This one is second choice. 0.6 is second choice. It is acceptable. If it is not possible for us to make it equal to a whole number, then we accept it as the scale we're going to make use of. That means that somebody can stop here and start using 0.6 to calibrate this axis. But I ask again, can we make it a whole number? If 0.6 becomes a whole number, what is the nearest higher number that is equal to a whole number after this 0.6? It is 1. That is, if I approximate this 0.6 a bit upwards, what you get is 1. Therefore, we target 1 to be our scale. That means if 1 is used as a scale and 0.6 is used as a scale, both are acceptable, but 1 is better. So I wish to make this 0.6 a better scale. I want to push it up to 1. How do I do it? We have 2 options, remember. The first option is to manipulate this 0.6. Second option is to manipulate this H or T if necessary. Any one you use will give you the same targeted value. Let us see how to make this 0.6 become 1. Don't forget that this 0.6 is not a wrong scale. We are just trying to make it an easy scale. Now watch how I have made the scale become 1. I had to manipulate this H, which had been 3. How did I do that? Since my intention is to make the scale become a whole number, I had to look for a number which 5 can divide to make equal to 1. That is how this 3 was pushed up to 5. This 3 was pushed up to 5. See it here. So scale is still here. Is now approximately equal to, no longer equal to, but now approximately equal to this 3 is now 5. Remember, it is by manipulation, just being discrete to manipulate. That is, what next number above 3, not so far from 3, can we place in place of 3, which 5 can divide to give us the 1 which we desire as the scale? It is 5. That is how this tree became this 5. So when 5 divides 5, the scale became 1. We are now using this 1 as the value of one interval along this x-axis. We could as well have done this thing by leaving 3 and 5 alone, so that after we get the value of this scale, which is 0.6, we approximate 0.6 to 1. Either way, the scale has become 1. That is all we can do with respect to this x-axis. Let's do the same thing for y-axis. Now, regarding the y-axis, we have values ranging from -19 to 11. So which one is this h? Is it -19? Is it -13? Is it -7? Is it -1? Is it 5? Or 11? Going by magnitudes, as earlier stated, the highest is this 19. So while choosing scale for this y-axis, I'll place this 19 to replace this h. But because we're choosing a scale for y-axis, this minus is going to serve us only a purpose. What is it? Knowing that the number with the highest magnitude lies in the negative region of the y, that is why we're going to make use of this side to choose a scale. We will not use this upper region to choose a scale. But don't forget that I said earlier that if I use this side alone to choose a scale, the scale chosen will serve the entire axis. Therefore, this minus makes us concentrate on number of intervals from here down. But this 19 makes us know that it corresponds to the number with the highest magnitude. Next is to get the number of intervals from here down. Let's see. Let's now count the number of intervals on the negative y-axis, counting from this place downwards. Follow me as I count. 1, that is from here to here is 1, 2, 3, 4. Let's mark this 4th position. Now we continue. 5, 6, 7. This is the edge of the graph page. Having done this, let us now choose a scale for the y-axis. The formula remains the same. Scale is approximately equal to h over t. Let us find the value of h for the y-axis and t for the y-axis. We recall that earlier we got 19 as the value of h. That means we're going to replace this h with 19. The minus sign with 19 tells us that it is this subaxis we're using to get the scale. And afterwards, the scale obtained will serve the entire axis. Let's continue. What about t? A short while ago, we got that the number of intervals from 0, that is from origin, till the bottom of the graph page was 7. Therefore, we had 7 intervals. Are we going to use all these 7 intervals? Certainly no. What do? We cut off either 1 or 2. Since we have 7, let us cut off 2, so that in all we have 5 intervals we're going to make use of. The extra 2 not used will serve us as emergency. Therefore, h is 19 and t is 5. Let us now find a scale for the y-axis and later determine if we must manipulate it to get a desired or preferred scale. Let's continue. Now we see that if this HE is 19 and this T is this 5, when 5 divides 19, we get that scale is equal to 3.8. What about this 3.8? Is it among the preferred scales? Surely 38 is an even number, and 3.8 is the first power 10 submultiple of 38. Therefore, it is as if this 33.8 is acceptable. But don't forget that I said earlier that those preferred scales are mere suggestions. That is one principle that overrules everything. What is it? Easy calibration. If we calibrate this axis with 3.8, though it is an even number, can it be used to the end without our having to need a device for calculation? The answer is no. Because of that, we have to push this 3.8 up to a scale or a value that would not make it difficult for us to calibrate. If you push this 3.8 up to the nearest higher number, which is acceptable as a preferred scale, what number could that be? It is 4. 4 is okay. 4 is an acceptable scale because it can be used to calibrate without needing calculating device. 4, 8, 12, 16, 20, and in that manner. Let's now consider making this 3.8 become 4. We have two options. Just approximate 3.8 to 4. That means we did not manipulate H and T. We had to manipulate the answer after we got it. That is the first option. Second option is manipulate the H so that the answer we're going to get is the same 4. Now, we can simply say that this scale is equal to 3.8, then approximately equal to 4. Let's see. See it here, approximately equal to 4. Alternatively, we push this 19 to 20 so that when 5 divides 20, the answer is 4. That's how this 19 became this 20. So that scale is approximately equal to 20 over 5. Therefore, scale is approximately equal to 4. So either way, either by manipulating the answer, that is 3.8, or by manipulating the value of H, scale is equal to 4. So far, we have seen that the scale for x-axis is 1, and the scale for y-axis is equal to 4.